Hello and welcome to another Hopper on 6502 video. At first glance it might not look like it's all about 6502 and Hopper, but this post that I saw yesterday caught my eye. Post by Gordon Henderson. He just finished a project where he just built another tiny basic for the 6502. And the thing that caught my eye was the 82 seconds, because I've become a bit complacent in how I measure the performance success of Hopper against the real world. And I'd been using the Civ benchmark for a while, the 1980 Byte Magazine Civ benchmark, where I can compare myself to the old basics. But it doesn't really test things like integer multiply and integer divide. It's pretty good at testing things like for loops and while loops and array access. But, this sort of pushed me in the direction of trying to do something, shift gears for a while on performance improvement. So let's have a look at Gordon's project. What does he say? Let's quote him. "Who would have thought that in 2023 some idiot would write another tiny basic for the 6502? Exactly, Gordon. That's exactly who we are, and this is what we do, and we do it because we can." Gordon's basic is only 3,700 bytes, and it's pretty rich version of tiny basic. It's not so tiny, got quite a lot of features. It's pretty impressive. Anyway, let's switch in to see what I did in the Hopper environment with this. So this is the Hopper console ecosystem. It's written in Hopper. This editor is written in Hopper. This is Gordon's basic source code. It took me a while to figure out what some of these things did. It's a bit cryptic. Thankfully, Gordon has a website with some documentation that I could read, which made it pretty quick to figure out. Let's go look at what the Hopper version looks like. Now, Hopper is a curly brace and semicolon language. So if you're familiar with Java or C#, or C++ or C, then this should look a little bit familiar to you. Anyway, this is the my port to Hopper of Gordon's tiny basic version. One of the cool things about the tiny basic version is that it's 16-bit integers. I forgot to mention that. That makes a difference. So you can do something on these small machines that's pretty significant, that looks pretty cool, but you're only using 16-bit integers. I make the horizontal range a little narrower because I want to fit it on the serial output in my debugger. I could try and put it on the screen, but I've only got a little LCD on my 6502 machine. It's only got 20 columns by 4 rows. So as part of the port, I created some output methods which emulate the same functionality that is in BASIC. So here they are. And you'll notice I've if-def'd them, so for conditional compilation. So when I'm running on Windows, I can output to the screen, and when I'm running on Hopper, I'll output to the serial port. So let's see let's just build it for Windows. So if I do that, and then I F7 here, I can build for Windows. Bottom of the screen, it's built a Mandelbrot.exe Hopper executable. That's the opcodes in the Hopper executable format for the Hopper virtual machine. If I go out to my console and I now type Mandelbrot, we will see the narrow version of Gordon's Mandelbrot. And it's pretty fast, 18 milliseconds. I think it looked longer because it takes a while for the screen to catch up. So that's what we're going to try and get onto our 6502 now. Now let's go back to the editor. We'll now switch to the other system unit. So now it's going to know to target 6502 when it compiles that. So now we press F7 again to build. And we've targeted the 6502 if you look at the bottom of the screen. Now we can go and launch the debugger here, F5. title bar changes from blue to green to show us that we've changed environments into the debugger. We're in the debugger. And this black area on the top right is the serial console from the 6502 machine. It says at the bottom left here that it has uploaded a .hex file to the 6502. That's the Intel iHex format for which to just do the transfer of the hexy file to the 6502 machine. I'll F5 to run it. It's now running on the 6502 machine, and we can see that the input is slowly coming in back from the serial port. Obviously not nearly as fast at 4.9152 megahertz. Strange clock speed. I was going to originally use that crystal for RS-232 port, but now I'm using it just as a CPU crystal. There you go. So that's what the output looks like. Now, for purpose of illustration, I'm going to hit F5 again. After it finishes and exits, it just resets for another run. So I'll press F5 again. We'll start again. I press Control C. Now I break in the debugger. Now I can single step through the debugger. And you can see on the bottom right, there's a call stack with one item in it, main, and the local variables in this window. Lots of single character variables, thanks to Tiny Basic. And let's press F9 over here, and we'll put a breakpoint in pink with a little red dot left of it on this line where it's going to output the next significant character, the next non-space character. So let's F5, and we'll get to there. We stop over there. Gray shows us the current position in the debugger where the debugger is. Current program counter in the virtual machine. So let's see what we've got here. Index is 0. It's indexed into this string. So that means the next thing that's going to come out on the screen is a dot. And it should appear where my cursor is. Let's press F10 and see if it does. Yes, we got a dot. All right. Let's carry on and stop at stop there again. Let's put out a few more dots. We're changing characters. F5, F5, F5. All right. Now I'm going to press F11, which is step into. All these shortcuts are on the menu, so step into. And we've stepped into this method. If you look at the call stack on the bottom right, we've now got two things on the call stack, the main and the method we're currently in. And as part of the arguments, we can see one of the arguments is a local variable, same thing. And we're about to output another quote. So if I press F10, we should get another single quote. And there it is. I think that is enough about the debugger. We've learned how the debugger works. Let's go back to the editor, Alt F4. And let's change the Mandelbrot to the full width that Gordon had. Rebuild it. And now I'm going to run it from the monitor. So there's the Hoppermon server runs on the 6502 machine. I can run the Hoppermon client on my desktop machine, on my Windows machine. I can here load Mandelbrot, and that'll upload the Intel hexy file to the 6502 machine. And then I can say X and it'll execute it. So this is the same idea, just I wanted a wider screen. So this is our entire serial port width across the screen here, running my Mandelbrot on the 6502 machine. With the clock speed here, we could compare, Gordon and I could compare performance of different machines. So he's got a 16 megahertz machine, I've got a 4.9 megahertz machine, and we could see the relative performance, compare apples to apples. He then went and ported it to another language and like a more commercial language so that we could see how Hopper is performing relative to that. And it's kind of inspiring because it shows you what's possible and how much room there is to improve. So between when I started on this little exercise and now, I've doubled the speed of 16-bit integer multiply and 16-bit integer divide. So 2 times improvement is pretty significant. Let me show you how. So I made this commit to the Hopper repo on GitHub. I'll share the link below the video. I've made it as an optional feature. It's about 400 bytes of overhead, which is a lot when you think that Gordon's entire Tiny Basic interpreter is only 3,700 bytes. But Hopper's about 20K, so 400 bytes seems like a reasonable sacrifice to get fast integer arithmetic. And it's optional. You can turn it on and off if you're not going to use it, you won't have that 400 byte penalty. How did I do it? Well, there were obvious simple optimizations like multiplying by 0 and 1 and dividing by 1, super shortcuts. And then powers of 2 are always kind of handy for both division and multiplication. And these are general improvements that don't just improve for this data set, but improve for all cases. Another common scenario is division by 10, which there's a lot of work being done over time to optimize because humans are decimal creatures. And it gets used in lots of other places in Hopper, like, for example, all the two-string APIs for integral values like longs and bytes and ints and uints. They all need division by 10. Once you've got a fast division by 10, you can repurpose it to get your division by 100 by dividing by 10 twice, and you can repurpose it to get division by 50 by dividing by 10, multiplying the result by 2, and then divide by 10 again. And that gets you a fast division by 50. And then the final thing I noticed is that a lot of the factors in the multipliers in this specific data set, both factors had 0 most significant bytes. So you could use an 8-bit by 8-bit multiply to get a 16-bit result. Now this has been beaten to death over the years, and the fastest version of that is actually quite ancient. Where did this all come from? Didn't just drop out of the sky. I used Google. I found existing work from lots of people, as you usually do. The 8 by 8 actually has some pretty ancient references from 1983. So that was the one piece of code that I got from somewhere else. I've given credit, and here's a link to the original. And the other one was the 16-bit divide by 10. So much noise on the internet on this one. Hard to kind of isolate when you found the best version that's reliable, that's small, and that's fast. And I believe this was the most optimal one. It uses two small tables at the end to correct the result to get perfect, as good as you can get 16-bit division by 10. Pretty cool. Anyway, I'm very happy with the progress, and I'm happy that I got shunted in this direction. So thanks, Gordon, for that, for giving me a little purpose here in terms of what to optimize next. And thank you all for watching.